Hello friends, welcome to the Siddha.com. Now here in this video we will learn about the relative stabilities of alkenes. Alkenes, we know they have a carbon-carbon double bond, and due to the pi electrons, alkenes are very much reactive, okay, because pi bonds can easily be broken down, and alkenes are very much reactive due to these pi electrons. Okay, we got a sigma bond and the pi bond between the two carbon atoms, and the pi bond can easily break down because this is a weak bond. So therefore, in general, alkenes are more reactive than alkanes. However, if you attach some alkyl groups to the alkene, the stability of these alkenes increases. So if you got here a very simple alkene, ethene, which has 4 hydrogen atoms attached to it, and if you attach now a 1 methyl group to it, it will increase the stability. This is the propene molecule. Propene molecule is more stable than ethene, and if you increase the number of alkyl groups, the more the substitution we do around a carbon-carbon double bond, more will be the stability of the alkenes. Okay, so if you have a one more molecule which has suppose 2 methyl groups attached to it, CH3 to this side, here in the first case you see that there is no substitution. Here in this case there is a 1 methyl group attached to it. Here in this case we find there are 2 methyl groups, and the stability of these alkenes increases as the number of these substitution groups, as the number of these alkyl groups increases. That means among the 3 molecules, the third one will be the most stable and the first one will be the least stable. Okay, least stable, and this is the most stable, and this we can find with the heat of combustion, right? Suppose you take one butene molecule. The heat of combustion, you know, when we react with the oxygen and form the carbon dioxide and the water, the enthalpy changes are different for the different molecules. You got here the but1ene, it has 1 ethyl group attached to it, only 1 alkyl group here attached to it. The heat of combustion here is 2717 kilojoules. Okay, but for the cis-2-butene, you know, we have here 2 alkyl groups, and we find the heat of combustion is less, right? Heat of combustion is less. It is 27101. So difference is 7. Okay, that means alkene, you know, this but2ene is more stable than the but1ene. Why? Because in the but2ene there are 2 substitution groups, and but1ene there is only 1 substitution group attached to a carbon-carbon double bond. You know, you got here a carbon-carbon double bond, and there in this molecule you got a carbon-carbon double bond, and it has 2 hydrogen atoms here, 2 hydrogen from this side and 1 from here, and it got the C2H5. So it has only 1 alkyl group attached to it. Trans-2-butene also, again you see a very small difference between the cis and the 2. No doubt the number of substitution groups is same. We'll talk about this one later on, but again you can see it's more stable, right? Now why the stability of the alkenes increases when we do the substitution? Okay, so let me explain it with this example. You got a carbon-carbon double bond, and if over here I attach a 1 methyl group to it, a CH3 group to it, it will increase the stability. And this can be explained with the help of hyperconjugation, right? Hyperconjugation. Okay. In this molecule, what happens here? The hydrogen atom here, right? You can see this is alpha hydrogen. We know for the hyperconjugation, what is the requirement? For the hyperconjugation, you should have a alpha hydrogen atom, right? Okay, so over here what happens, the double bond breaks and it shifts towards this side. Here you get a double bond and you get a resonating structure like this. Carbon, hydrogen attached to it. Now you got a carbon-carbon double bond over here. Now H plus here, hydrogen is over here, and you got the single bond and then the negative charge on this carbon, right? So this is the one resonating structure. This is the second structure, and then this will shift here. The pi, this electron, the sigma electron, they will shift over here, and you get a structure like this. And you got the H plus over here, right? And then in another structure, you can see the electrons from here, they will shift towards this side, and the positive charge will be on this hydrogen. So simply, this is the same concept that we have learned in the hyperconjugation. I hope you have understood this one, right? You got the H plus here, and we got a double bond over here, and then the hydrogen here, and then a single bond, hydrogen, hydrogen, and the carbon with negative charge, right? And then again this electron pair will again go back, and this will go back, and what you get the first one back, right? So from the third structure you got the fourth one, and from the fourth one you got the first one back. Due to this resonance, right, resonance of the sigma electrons, right, this is what we call hyperconjugation, isn't it? So this is the resonance of the sigma electrons here. You got the sigma bond, the alpha bond here. Okay, alpha electrons, they get delocalized over here due to this double bond, and you can see due to the resonating structures the molecule attains some stability, correct? So that means if you attach an alkyl group to it, to the carbon-carbon double bond, it will increase the stability, and higher the number of these groups, more will be the stability. Suppose if you do a one more substitution over here, okay, so you can get more resonating structures in this molecule. With the one methyl group only, you got 3 more structures. With the 2 methyl groups, you will get 6 more structures. Okay, so higher delocalization means more stability, correct? That's why when you increase the number of methyl groups around a carbon-carbon double bond, the stability increases. That's why we found here in our previous, in this one, we find that when you increase the substitution here, right, when you increase the substitution, the stability increases, correct? The stability increases because the energy released here is less. That means this is more stable. But2-ene is more stable than but1-ene because here the energy release is more, here the energy release is less, right? So but2-ene is more stable than the but1-ene because you got here the 2 double bonds, 2 methyl groups, 2 substitution groups. Here you got only the 1 substitution group. So in this case you will get less number of resonating structures, hyperconjugation structures. You got here more number of hyperconjugation structures, right? But why, in this one, in the cis and the trans, in the cis and the trans, you see the number of groups is same, 2 methyl groups, 2 methyl groups. So if the number of groups is same, then why the cis one is less stable than the trans? Why the trans is more stable if the number of groups is same? The reason here is different. The reason here is the steric repulsions, right? In the trans molecule, the groups are away from each other, the repulsion will be less. In the cis configuration, over here, the groups are closer and the steric repulsion will be more. You got a methyl group here. This is another methyl group. This is the carbon-carbon double bond over here. Suppose you got a carbon-carbon double bond over here. The 2 groups in the cis position, they are closer, so steric repulsion will be more. Over here in the trans to butene, the 2 groups, the 2 methyl groups here are away from each other. You got a carbon-carbon double bond. The 2 methyl groups are opposite, right? The distance is more between the 2 groups. The repulsion is not so high as you find here, right? In the cis, they are closer, so more repulsion means it will be unstable, right? Here, the groups are away, so it will increase the stability. That's why the trans is more stable than the cis 2-butene. Okay? Fine. Hope you got the concept. Thanks for watching the video. Bye for now.